Welcome to my next 3 objectives for Module 3. So this is carrying on with the topographic mapping. So the first thing we're going to cover is Objective 3.4, which is calculating slopes on a map. So slope, as you may remember from math at some point in your life, that slope is calculated as rise over run, which means that it is the change in elevation divided by the change in distance. So delta y over delta x. So the change in elevation, that little delta or the little triangle is delta, which means change. So we are going to be looking at calculating a slope over a distance. So this is why calculating scale comes before calculating slope, because we need to know scale in order to figure out the distances. So we have 2 different ways of looking at slope. One is just looking at the slope value, which is often a decimal place, or we can do a percent, which it means that we just take that slope value and we multiply it by 100%. So here's an example. So you are planning to head out to do some mountain biking. So I don't know how many of you do mountain biking, but I'm sure there's a couple of you that have at least tried it. Your trailhead starts, which is the beginning of the trailhead is like the beginning of the route, starts at 1,012.4 meters above mean sea level, and the peak of the trail is at 1,398.1 meters. You measure that the distance of the trail is 28.7 centimeters from the trailhead to the peak on a 1 to 20,000 map. What is the slope and grade that you need to climb to start your ride? Okay, so first things first, we need to figure out the actual distance because we don't know that yet. So in order to figure out the distance on the ground, we have to use the scale information and the map information, to map distance, to calculate our scale. So we have 1 over s equals dm over dg, and so that equals my 1 over 20,000 equals 28.7 centimeters over dg. I can cross multiply and divide, so I go 20,000 times 28.7 divide by 1, and I get a ground distance of 5,740 meters. So now that I have the difference in distance, I need to figure out the difference in elevation. So here my delta elevation, I always I always start the equation or subtraction with the last point. So if I start somewhere and end somewhere, it's the ending point that I am calculating. So, or using at the beginning, I calculate with that. Then I do the beginning. So you always use the end minus the beginning when you're trying to come up with a distance, because at this point, this is where directions are really starting to become important. Because if I have a negative, that means I've gone down in slope. If I have a positive, that means I've gone up. Those are 2 very different directions. In fact, they're opposite. So you need to make sure that you really have your end point first in the subtraction, and then you have the starting point second. So my delta elevation is my peak minus my trailhead. So I have 1,398.1 meters minus 1,012.4 meters divided by 5,740 meters, which was the distance I calculated from the map. And then my slope is 0.0672, or the grade, which is percentage, is 6.72%. So you can, depending on what I ask for, you're going to have to either use the percentage or the slope, okay? So the slope value. So most people like using percent because it is an easy number. 100% grade is a straight down. Like actually 100% is kind of an equal value. So trying to keep in mind that the grade percent sometimes is hard to interpret. But we do see grades all the time on roads, right? It's like, oh, you have a 6% grade. And so we'll see that as well. So it is more common to see percent, so we tend to put it in percent. But if I just ask for the slope value, then I'm just looking for the decimals. So no percentage on it. All right, so applying break lines to contours on a map. So this is kind of taking a detour from the slope concept of math, and we're going into the actual representation of contours and representation of features on a map. So what a break line is a invisible, usually invisible line on a map where the slope rapidly changes and two planes come together at that line. They're at different angles from each other, so therefore we're trying to make a clean, crisp location where that happens. Break lines are usually based on like either water features or they're based on some sort of man-made feature. There's a defined location where it happens, maybe like a peak. There's a peak of a hill that we really want to define and say this is the actual top of the hill, and so therefore all the contours are going to stop at this location along the line, not just at a point. So that's kind of where we sometimes put at the bottom of the slope. So the example I'm showing here shows it at the bottom of the slope. So they are important just because you don't want the contour showing like really strange edges, and so it makes things a little bit easier. You don't actually see a black line on a map. So here's just it's showing an example of where it would be, but it's not actually drawn on the map. So, but we can find, you can look for it on a map and just looking for these sharp changes in contours. So along here, we can see in this area that the contours along here, along this water body, kind of peak out, and we say that we do not draw them across a water body. In this case, because it becomes a break line. So it's just something to keep in mind. You can also see down here along the roads, you're going to see that the contours kind of change in funny directions along the roads. And that's because the edge of the road is actually a break line. So those are drawn on, but that's because they're drawn the road, and we want the contours to make sense along the road. So you can see that also like as we go lower here. If you look at your maps, you will definitely see some changes very similar to this, especially along roadways, along man-made areas. It's where those contours make those quick changes, and they are at the same location in the line, right? So it's an obvious cut. Where over here, like you can't really, there's no real break lines over here because it's a natural area. And we have the top, which it's actually indicating at the peak of the hill, this Caddy Hill. It's 1,122 at the peak. But as we go down, like there's nothing that really needs to be defined as a break line. So just something to keep in mind for the break lines. And when you're looking and you see some strange things happening with contours, it's not necessarily that that is naturally looking like that. It's because they've had to put in a break line for whatever reason. Break lines are really important in engineering applications as well, because it's like put it here because this is where the slope changes and you're going to minimize your cut and fill as much as possible. So Objective 3.6 is interpolating between contours. There will be a second video on this showing it a little bit more in action using a map, but I want to go through the math in this case. So contours are only about 1/3 of a contour interval accurate, which means that if you have a 100-meter contour interval, it means that only about 33 meters of it is accurate. So if you go to about 1/3 of a contour, that's about as accurate as you're going to get. So you have to keep that in mind as you're working through. Sometimes you'll see, oh, contours are about 1/5 or like 1/5 of contour interval accurate. I've seen that in the odd book, but for the most part, it's about 1/3 of the interval. Just because you're dealing with like rulers on maps or like mouse when you're like a mouse when you're pointing at things, you're dealing with pixels, you're dealing with line thicknesses, you're dealing with all kinds of stuff. So that's why the accuracy is only about 1/3. Precision might be a bit different, but accuracy is that. So when you're interpolating between contours, what interpolation means is the the prediction of a value that is, or not a prediction, but an estimation of a value between 2 points. So it has to be within those points. It can't be without, like outside. We call interpolation is in between, extrapolation, not extrapolation. Extrapolation is outside of a range of numbers. So we're always looking between 2. So for this one, we find the point that we need, that we're looking for, the elevation. Then you measure a straight line through the point and the nearest contours on either side, as perpendicular to the contours as you can get. Okay. Then you're going to use the following equation. Now this is like a little, it really like takes it further for those of you who love equations. But what we're trying to do when we're doing contour interpolation is you get that line and you figure out what is the actual distance from one contour to the next. And you say, okay, it is from one contour to the next is 1 centimeter. My point is about 2.5, 1 centimeter, so about 2.5 millimeters from the edge, okay, from one of the edges. So then what I do is I divide it in half. So that means that my 1 centimeter is now 0.5 centimeter, and I'm right in the middle between. Now, I'm going to decide what side of the contour line, what side of that middle line is the point that I'm trying to figure out. Is it closer to the higher number, or is it closer to the lower number? If it is closer to the lower number, then I'm going to take that half and I'm going to divide it again. So now I'm at that like 1.25 millimeters, right? So I'm really like trying to get super precise in that case. Oh, sorry. I totally did the math wrong. So I've dividing it way more than what I need to be doing. So 1 centimeter divided in half, you get 5 millimeters. Then those 5 millimeters, you're going to divide that in half because you're going down to like the lower value, like I was saying. So now you're at 2.5 millimeters. That's a little bit better. I'm like, wow, boy, did I ever get really small. So we're 2.5 millimeters. So that 2.5 millimeters, it gets close enough to that point. So I'm like, okay, it's close enough to the 2.5 millimeters, or is it close enough to the, like right on the line, or is it closer to the halfway point, right? So now I got to kind of decide where is it closer to. And then once I've figured out which of those, then now I can try to determine what is my elevation. So I'm going to take that contour interval, I'm going to divide it in half. So if it was 10, now it's at 5. And then I divide it in half again, now it's at 2.5. So my contour interval to that point is about 2.5, let's say, meters. So then if that's the case, now I go to my lower value, which was what it was, and I add that 2.5 meters. So let's look at a little bit of a visual here. So that was a lot of talking and very little visual. Okay, so here's my point in between 20 and 40. So if I were to put my, divide this into half, right? So I'm going to measure this distance here. I'm going to find out where the halfway point is. So I find out the halfway point is about here. Then, so now my new value is here. Now this is on the higher side of that value. So I know that the dividing it in half from here to here it doesn't fall in there. So it's in this higher half. So I know that the center point is an elevation of 30 meters, right? Because it's halfway between 20 and 40. Then I'm going to divide this lower part, or sorry, I guess it's the higher value. These are upside down, by the way. They should actually be flipped. That's why I'm going to have a trouble with this, and I'm just using this example from this web page. So you divide this again, and you draw this line divided into a quarter. Now what you're going to do is decide, is it closer to this quarter of a contour line, or is it closer to the halfway point? Now in my interpretation, I would say it's closer to the halfway point, because again, it's only a third of a contour interval accurate, right? So this is closer to this point, so I'm going to say, okay, it's about half. So you know what? I would say that it falls between 20 and 40, so therefore it needs to be about 30. Okay.
It might be a little bit higher, like 31 or 32, but that's what we're going to say. So ignore this because it shouldn't be 12.5 feet, unless this is in inches. But anyway, so that is how you would do that estimation of that where that point is located. So again, if you are looking for more information, please go ahead and take a look at these references. There's like breaklines and surface modeling, get a lot more information on it for that. And this one is looking at different maps. It's a geography class, but it's got a lot of really good stuff here too. So I highly suggest taking a look at that if you're really interested and learning a little bit more about topographic mapping. So again, there will be a few more other like short videos showing how to do things with like hands-on with a map, so please stay tuned for that.